Hit record. Okay, so y'all, I'm just going to do 2 problems today out of 4.7. Um, the homework for 4.6 is up and ready, y'all. It's due by next Monday night. 4.7 is up and ready too, but it's not due until next Wednesday, okay? Because we're going to finish it up on Wednesday. I just want to do 2 problems because these problems do take a little bit of time to do. The first one I think is a little bit more complex than the second one. The second one is going to be a pretty straightforward type problem, but this one does take a little bit more time to do. 4.7, y'all, are applied optimization problems. And I want y'all to think about for a second the word optimization. Optimization, y'all, means we're going to be looking for one of two things. We're either going to be looking for the maximum or we're going to be looking for a minimum. Okay, that's what the word optimization means. We're going to either maximize something or we're going to minimize something here. So let's take a look at the first problem, and it says a box with a square base and an open top must have a volume of 500,000 cubic centimeters. We wish to find the dimensions of the box that minimize the amount of material used. So remember what I told you, optimization, y'all, are either going to be maximums or minimums. In this case, we're looking for a minimum, okay? And so the directions here say, first find a formula for the surface area of the box and only in terms of only x, the length of one side of the square base. Okay, but they do give me a hint. It says use the volume formula, to express the height in terms of x. Okay, so let's figure out what's going on here. We have a box and it's an open top box, okay? And the base is the square base. So look, let's think about it like this. Look, y'all, I'm going to draw a square base. Okay, so look, here's the base of my box, x and x. And the box has a particular height. I don't know what that height is, but the height of the box is going to look something like this. Not too bad. Okay, so let's call the height of the box, let's call it y, okay? Because I don't know that the height of the box is the same as the base. I do know that the base is a square base because they tell me that right there, right? It says it's a square base. Question, does anybody remember the formula for the volume of a box? Going once, going twice? Okay, if you don't, that's all right, don't sweat it. The volume of a box shell is a straightforward formula. Look, it's the length times the width times the height, okay? So in this case, let's find our volume. The length is x, the width is x, and the height is y. So x times y is the same thing as x squared y. The other thing that we know about the volume of the box is the volume is going to be equal to 500,000 cubic centimeters. So take a look, y'all. The volume here, I'm going to do this on the side. The volume is going to be equal to 500 cubic centimeters. Okay. What I'd like for us to do here, y'all, is I'd like for us to solve this equation for the letter y. If I were to solve this equation for the letter y, do you all agree that I would end up with 500,000 over, say, x squared? That would be my value of y, right? Just solving for y, dividing everything by x squared. Okay, second thing we're going to do, we're going to find a formula for the surface area. The reason why I want to do that, look what they tell me right here. It says, find the formula for the surface area of the box in terms only of x. Okay, so surface area. Think about what the surface area means. The surface area is if I wanted to find the area of all sides of that box and then add them up, right? So look, here's the base. If I was thinking about the area of the base part, the bottom part, y'all agree the area of that would just be x squared? Okay. Now, I want you to think about the area of the side. So look at the area of this side right here. Kind of like this right side. what would the area of that square look like? Anybody know? What would the formula of that? Wouldn't it be xy? Okay. Wouldn't the area of this one here also be xy? Right? Because I know this piece right here is also y. And then wouldn't the area of this back one over here also be xy? And then wouldn't the area of that one over there also be xy? How many xy's did we have? How many sides? 4 of them, right? So plus 4xy. Y'all, one thing I want to mention, why do we only have one x squared? Because it's an open top box, right? There's no lid to the box. That's why we only have one of them. If the box would have been closed, we would have had an x squared on the top and an x squared on the bottom, we would have had 2 x squareds, right? But they told me it was an open area box. Okay, 4.7. So now look, what we're going to do is we're going to write a formula for the surface area, but only using the letter x. And right now, y'all, we do have a y in here. So look, this is what we're going to do. We're going to write surface area is x squared plus 4 over x times, look what we said y was. Y was 500,000 over x squared. Okay. So now my surface area is going to be x squared plus, y'all, wouldn't this x reduce with one of those x squareds down there? So 4 times 500,000 should be something like 2 million over an x, because 4 times 5 is 20, and then I had 4 zeros, or 5 zeros, so here's my 5 zeros, and then this x cancels with one of those. All right, so now look, I found a formula for my surface area right here, okay? I'm going to come back to the problem, and I want you to notice what they told me to do. Can we write a formula using only terms of x? Yes, we did. It's right here. So I'm going to write over here, y'all. Hold on, y'all. My OneNote froze. It is? Yeah, no, but the thing is frozen. Hold on, y'all. I don't know why this thing froze. Oh, okay. All right, I guess it shut down. Let me see if it comes back up. There we go. Okay. So let's see. Here's my formula for the area: x squared plus 2 million over x. I'm going to write that in, y'all, right here. X squared plus 2 million. And I'm going to actually write it like this, y'all. Can I write it as x to the power negative 1 if I have an x on the bottom? Right? So I'm going to write it as x to the power negative 1. The reason why I want to do that, look at the second step. It's telling me, can we find the derivative? Okay, so look, if my surface area, y'all, is x squared plus 2 million x to the negative 1, and I now want to find the derivative of that. What would the derivative of x squared look like? 2x. Okay, what about the derivative of 2 million x to the negative 1? Negative 2 million x to the negative 2. Very good. So look, y'all, that's what I'm going to write over here. We're just taking the derivative. 2x minus 2 million x to the negative 2. Okay. All right, now look what it says next. It says, now calculate when the derivative is equal to 0. Okay, so I'm going to take my derivative, y'all, and we're going to set it equal to 0. So 2x minus 2 million. I'll write it like this, y'all. Right now, I'm going to set it like this, is equal to 0. Okay. So if I'm trying to solve this equation for the letter x, a couple things I can do. If we take this term here, y'all, and we move it over to the right side, y'all agree that we would end up with a 2 million over x squared? And can I think of this 2x as 2x over 1? And the reason I want to think about it as a 2x over 1 is because when I have one fraction equal to another, can't we now cross multiply? So question, what is 2x times x squared? 2x to the third. And 1 times 2 million is still 2 million, right? Okay. Guys, how do I get rid of the 2? Divide it out, right? So 2 million divided by 2 is a million. Okay. Question, does anyone know how would I solve this part for x? If I have x to the third is equal to a million, how would I find the value of x? Anyone know? We're going to take the root. Very good. Excellent. Thank you, Jennifer. We're going to take the root, y'all. Y'all, since we're dealing with x to the third, we're going to take the cubic root. Okay. So, y'all, I'm not sure if you remember how to do this on your calculator or not, but if you're going to do this on your calculator, I have 1 million. And actually, I'll do it like this. I'm going to put it in parentheses. 1 million, 2, 3, 4, 5, 6. Okay, so my calculator doesn't have like a cube root button or anything like that, but it does have a power button. Yes, that's what the cube root means, right? So so think about it this way, y'all. The square root means you're getting pairs, right? So if I were to ask you, like, what's the square root of 25? You would tell me 5, because a pair of 5 when you multiply them, right? 5 times 5 gives you 25. The cubic root means instead of getting pairs, now I'm looking for triples. What number, when I multiply it by itself 3 times, would give me a million? What you can do, y'all, is you can use the power button when you're dealing with roots, like the cube root, the fourth root, the fifth root. You can raise it to the power 1 divided by whatever that root is. So I'm looking for the cubic root. I can do this as the power 1/3. When we do this to the power 1/3, look at the x value that we came up with. Came up with 100. What does that mean? 100 times 100 times 100 would give me what number? A million, right? Okay. So look, we came up with our value. We came up with x being 100. Okay. Y'all, I'm going to scroll back up to the top of the problem, and it says, look, find when the derivative is equal to 0. Hey, we found it being equal to 100. Okay, now it says we have to make sure that this value of x gives us a minimum value for the surface area. Let's use the second derivative test. So now we want to find the second derivative. Okay, look, y'all, right here is my first derivative. I'm going to copy this down, and then we're going to find the second derivative, okay? So let me do this over here on the side because I'm kind of running out of room. So the first derivative was equal to a 2x and then a minus 2 million x to the negative 2. So if I'm going to find, yeah, me too. So if I'm going to find the second derivative, what's the derivative of 2x? 2, right? Okay, what is the derivative of a negative 2 million x to the power negative 2? Positive 4 million, very good. X to what power? Negative 3. Okay, y'all, I'm going to write it like this now. X to the third on the bottom, okay? What are we going to do now? We're going to evaluate this at 100. So remember what that means. All that means I want to do is everywhere I have an x, I'm going to plug in what number now? 100. Okay, right? All right, so let's do this. So let's do the first part. Let's do the 4 million, 1, 2, 3, 4, 5, 6, divided by 100 raised to the third, and that's 4 plus 2 is 6. Okay, so when we found the surface area, the second derivative of the surface area at 100, we came up with right? Okay, I'm going to scroll back over here, y'all. Scroll back over here. We found the second derivative. Oh man, what was it equal to? It was equal to like 2. Yeah, but 2 plus 4 million over x to the third. So that's what I'm going to plug in right here. 2 plus 4 million over x to the third. And then when we did it, we came up with 6, right? Okay. Remember, y'all, when we evaluate the second derivative at the critical value that we came up with here, if that number is positive, then it's giving me a what? It's giving me a minimum, right? If the second derivative of that value happens to be positive, then we're coming up with the minimum. Okay, so y'all remember what it is we're trying to find. Let's scroll back to the top of the problem. I'm going to look right here. We wish to find the dimensions of the box that's going to minimize the amount of material used. So we found the value of x. The value of x that was going to make this a minimum was when x was equal to 100. Okay, so look, I'm going to come back over here. I'm going to look at my picture again. I'm just going to kind of redraw it because I drew a lot of business on there. But I want you to think about what my picture looks like. It looks something like, messing it up. It looks something like this. X and X, and we'll make it a little bit taller. I wish I was a little bit taller. Okay, so there's my Y. So we know that the value of X on the bottom is equal to 100. We still want to find the value of Y, okay? But look, we have a formula for the value of Y. Y is equal to 500,000 divided by X, which is 100 being squared. So now, if I take, fill this out, if I take 500,000, 3, divided by 100 being squared, my Y value is 50. So what are the dimensions of the box? 100 by 100 by what? By 50. So guys, one thing I want to mention is when you're looking at the problem, I mean, when I came back to the problem here and it said we want to find the dimensions, I want you to look at, and I copied this verbatim, y'all. So I did like literally copy and paste from my open math, right? But let me ask you a question. In any of the little answers that I have here, did I ever have to fill in 100 by 100 by 50? No, right? It's kind of silly, but I never actually had to do that. These were literally the steps that I had to do, but just to kind of like follow through with what the problem was asking me to do, right? Because the problem was asking me, can I find the dimensions? Well, we were able to find the value of x, which was the square base, right? So since we were able to find the square base, then yeah, it was easy for us to find that height of the box, right? But in the actual problem, and again, I copied this verbatim, it never, it's kind of silly, but it never actually asked me to list, you know what I mean? It never actually asked me to list those dimensions, right? It just said, do these steps, and we did them, but we never really answered the question unless we would have done that part ourselves. You see what I mean? But I kind of wanted to go through it because that's how it makes sense. It's just a little silly that they didn't actually ask me to list those values in my actual answer. You know what I mean? All right. So again, this is why I say this problem is probably like the more. And there's, when we come back on Wednesday, we're gonna do 2 more problems that are like almost identical to this one, just so we kind of start getting the habit and trying to figure out like, okay, how am I doing this? What's the process? But I just wanted to show you one of them today. We're going to do another 2 problems almost identical to this one on Wednesday. But this is like the more, between the 2 problems we're going to do today, this is the more complex one. Okay, so if it's still kind of a little shaky, when we come back on Wednesday, y'all, we'll revisit some of this stuff again. Surface area was x squared over plus 2 million over x. Okay, so look, y'all, I got one more problem that I want us to do, and then again, we'll call it a day here, and we'll pick up the rest of 4.7 on Wednesday. Um, but I'm going to ask you a question here. So let's just read through the question and see if we can't figure out what's going on here. It says an object is thrown. T seconds after it's thrown, its height is given by this equation right here. So I want you to notice something. They gave me a function, h of t, okay? And h of t is equal to negative 16t squared plus 288t plus 450. And it says the object reaches its highest point after how many seconds, and then what was that maximum height? So y'all, remember what I told y'all? 4.7 talks about optimization, right? And optimization means we're either going to look for a maximum or we're going to look for a minimum. And in the problem that we did before, look what the direction said. We wish to find the dimensions of the box that are going to minimize, right? So that's how we, like I told you, it's going to be one or the other. When I look at the next problem here, we're looking for the object's what? Maximum height. Okay, so it's, again, it's always going to be one or the other. It's either going to be a maximum or it's going to be a minimum. Okay, question. Does anybody remember what, because this is a quadratic equation, right? Because it's quadratic because it has two squares. Do you remember what graphs of parabolas look like? Yeah, they either open up like this or they open down like that. Okay, now, y'all, anytime the leading coefficient, remember what the leading coefficient is? The leading coefficient is the number in front of the leading term. The leading term is one that has the highest exponent. It's not always the one that's written in front, but it's always the one with the highest exponent. Since the highest exponent is 2, the leading coefficient is a negative 16. If that leading coefficient is negative, my graph opens down, and if my leading coefficient is positive, my graph opens up. So if the graph opens down, do y'all agree that this point here would be the maximum, right? Okay, so what we're going to do, y'all, is we're going to find the first derivative, okay? So the way we're going to find the first derivative, y'all, is we're going to take the derivative of this function right there. Let's do it one piece at a time. What's the derivative of negative 16t squared? Negative 32 with a t plus 288, right? And the 450 goes away. Okay, remember y'all, we're going to find our critical value now. The way we find the critical value is we set the first derivative equal to 0. So we're going to take negative 32t plus 288, and we're going to set that equal to 0. When we do that and we move that 288 over, does everybody agree that that becomes a minus 288? Because I'm crossing the equal sign? Okay. Last step, how do I get rid of my negative 32? Divide it. Perfect. Very good. Because it doesn't matter which one I move. Yeah. You're solving an equation. What term do you get on one side, on the other? It don't matter. 288 divided by 32, 9? Very good. Thank you, Steve. So we come up with t equals 9. Okay, that is the t value. Okay, that's the time when we're going to hit that maximum height. So look what it says. The object reaches the highest point after how many seconds? In this case, 9 seconds, right? And then part B, what is that maximum height? What we want to do, y'all, we want to find h of 9. So we're going to come back to the original function we have, and everywhere we have the letter t, we're going to plug in what number? We're going to plug in the 9. So 16 times 9 squared plus 288 times 9 plus 450. And I'm coming up with 1740. There you go. And there's your maximum height. Or a large stone, right? So yeah, if there's an object is thrown, what did they throw it with? Yeah, pretty high, right? So probably would have been a better phrase to say an object is launched, right? Something like that. Yeah, and that's all. Yeah, and that's all you're really doing there, y'all. So you can see that the second problem definitely much less time consuming than the first, right? So y'all, again, we'll pick up the rest of 4.7 on Wednesday. So I want to show you something. This problem here, look, a box with no top. Ooh, that's kind of like the first one we did. So we're going to do another problem like this. Um, let's see. Yeah, there it is. It's just kind of, I don't know why it's a little delayed. Yeah. Look, a box with a square base and an open top. This is exactly like the one we just did a little while ago. And then this one is new, a cylinder can, so we're going to have something new there. And I think that's it. Okay, so there's just three more problems left to do. But the first two, y'all, are very similar to what we did today. And then the other one is going to be slightly different, but again, we'll work it out together. But again, we'll reconvene with some of those ideas, and then we'll also do 4.8. Okay, so let me go ahead and stop recording because we